Okay, let's talk about rearrangements, and then we'll start into E2. I haven't checked the video yet to see why the E2 video doesn't work or if it's on the wrong link, so I will do that after class. But let's start with rearrangements and kind of take care of that. So rearrangements, these are called carbocation rearrangements. Or they're also called either hydride or methyl shifts. So this is a phenomenon that can happen, and there's a couple of caveats that I will just raise with this. Number one, they don't occur as frequently as any book would show you. You really have to kind of do the experiment to see if they do undergo these shifts. So I have to tell you when I would like you to shift on an exam or on a problem set. So I will tell you, write the rearranged product, or I'll give you a rearranged product, and then if you're fitting the mechanism to that, you know you have to do a shift. The part of the problem is, and I don't think Top Hat has this issue, but most textbooks, the books are written by one person and the study guides problems are written by another. So usually the book presents shifts kind of as they don't occur necessarily all the time, and then you go to the problems and they're all over the place. So I have to tell you when to do a shift. And so what is this carbocation rearrangement? What is this methyl or hydride shift? And let me give you an example that really happened when I taught down at OU. So what we did was we weren't really doing an E1 reaction, and it wasn't really an SN1, but what we were doing was we were reacting this molecule, this particular molecule, which is 1, 2, 3, 4, 5. No, that's not the correct one. It's this one. It was isobutyl chloride. And so we took isobutyl chloride and we were reacting it in a reaction I'll show you next semester. But here's what can happen with a primary system. So with a primary system, you can't lose the chloride. Let's say I was to react this with water. We know that water has to react by a carbocation rearrangement. So normally this would be a no reaction. Primary, weak nucleophile, no reaction. But if we heat the system up a little bit, we can get it to react. And how's it going to react? If the water can only react with the carbocation and the primary system can't lose the chloride to form a primary carbocation, what happens? And what happens is this shift. So if we take a hydrogen or a methyl group that is next to the carbon with the leaving group, so this is really kind of a beta carbon phenomenon. What can happen in this case is that this hydrogen can take its pair of electrons and move to bond to that carbon. Now, when that hydrogen is moving, it is moving as a hydrogen with two lone pairs, which makes it a hydride. That's the name. And so we would call this a hydride shift. So it's moving as an H minus. Now, if it just moves as an H minus, the chlorine has to leave. So what we end up with is we end up shifting the hydride over and the chloride leaving all in one step. And the transition state for this would have the hydrogen partially bonded to each of the two carbons. And then it would have the chloride leaving. So we're doing the same thing we had done before, which is partial bond to the bonds that are being made and broken. Now, in the end, we'll come back and do charges. In the end, what's going to happen? In the end, what's going to happen is the hydrogen moved to bond to that CH2, and the chloride left as a leaving group. Since the hydride picked up its pair of electrons and moved, that puts the carbocation in the tertiary position. Okay. And so this would be how that carbocation could then react with the water. Now you would get a tertiary carbocation. The water would come in and add to that, and you would make your alcohol. Okay. So in terms of charges then, really the charges in this transition state are going to be a delta minus on the chlorine and a delta plus on that carbon that's becoming the carbocation. And the reason the hydride has to shift and you lose the chlorine at the same time is you can't form a primary carbocation. Okay, so this is an extreme example of a hydride shift with a primary system. So whenever you have a primary system, you have to shift and lose the chloride all at the same time. And then that carbocation will go ahead and react with its nucleophile, or it might lose a proton to form an E product, etc.
So the carbocation does not have to be like the carbon that has the leaving group attached to it always?
It will be the beta, it'll move to the beta carbon if you do a shift. So in a lot of the problems that you were looking over for Monday's exam, you may have seen, because I got some questions like, why is the carbocation here and not on the leaving group? It's because that molecule underwent a shift. Okay. So in this case, what happens is you get a new alpha carbon. After the shift, you have to re-identify the alpha carbon and the beta carbons and the beta hydrogens to form the E1 products, if that's what you're writing. So in this case, what I'm doing is I'm showing you a reaction where we're taking a primary plus a weak nucleophile. Our chart would say no reaction. But if I said write the rearranged product, now what I'm saying is this alkyl halide can rearrange to form this tertiary carbocation, and now the water would come in and add. So we would have then two steps, right? We would have our two steps to form the final product, which would be tertiary butyl alcohol. And so this rearrangement is something that can occur. And anytime you have a primary carbocation, anytime you have a primary system, you cannot form the primary carbocation, so it shifts and leaves at the same time. So if I asked you to do a rearrangement on a primary system, the mechanism would look similar to this. Now, why does this happen? What's the driving force? And what are our rules? Our rules are this. Number one, the shift must result in a more stable carbocation. So when you do a shift, you have to end up with a more stable carbocation. You can't, in this case, we're shifting to go from potentially a primary carbocation to a tertiary. I'll show you examples in a minute or two. We can go from secondary to tertiary. We could, in theory, go from primary to secondary in this system as well. But you cannot go secondary, secondary. You cannot go tertiary, tertiary. This costs energy, and you need to get that energy back. And the way you get the energy back is by forming a more stable carbocation. So that's rule number one. Whenever you do a shift, you must end up with a more stable carbocation. If not, it's not going to rearrange. And rule number 2 is only one shift. Chaos, total chaos would ensue if you could just keep shifting down the line until you found like a tertiary system. So you only get one shift. And that shift has to obey rule number 1. Because you could say, well, couldn't I rearrange multiple times? No. Not under our rules. So those are the rules. This is sort of the exceptional system because this is kind of extreme. There's no carbocation to begin with that we're shifting. We're shifting from a primary system into a tertiary or a secondary carbocation. Now let me just show you, because this one worked. This one does work. So what happened was that you can make let me just show you, you can make carbocations by doing this. By taking alkyl chlorides and adding something like aluminum trichloride to them, or adding something like iron trichloride to them. We'll learn about this reaction next semester. This is called a Friedel-Crafts reaction. But what happens is that the aluminum or the iron, you can break the carbon-chlorine bond and you can give the chlorine to the iron or to the aluminum so that on the other side you would make something like AlCl4 minus or FeCl4 minus. So an easy way to make a carbocation is to react an alkyl halide with aluminum or iron. Another way to make it is to just use silver. So if you remember from general chemistry, silver chloride is insoluble. So silver bromide is as well. So if you were to add silver nitrate to an alkyl halide, if you form a carbocation, you see the silver chloride or bromide precipitate out of solutions. And I think there's probably videos on YouTube, because there's videos on YouTube about everything, but I think they probably lined up a primary, secondary, and tertiary halide and then added silver nitrate to it, and you can watch the tertiary form the precipitate first, then second for the secondary, and then the primary never does. So it's an easy way to tell whether something will form a carbocation. It can be a visual test. But you can also use iron and aluminum. So what we were doing in lab was we were supposed to be taking tertiary butyl chloride and reacting it with iron trichloride to make a carbocation that then we were going to add to a benzene ring, which we'll learn about next semester. So halfway through the lab, a young scholar down there said, hey, this bottle says that we're using isobutyl chloride and not tertiary butyl chloride, because I had inadvertently grabbed the wrong one from the shelf. And I said, no, it really doesn't matter. So then they pressed the issue a little bit by saying, well, what do you mean it doesn't matter? We're going to get a different product. And I said, no, not really. If you remember back to lecture, we'll get the same product. And then they continued. So I said, this is going to be a post-lab question. You're going to write the mechanism of how we get the same product. And it was because that shift really did occur. And so I can guarantee you this one occurs because we've done it in the lab. Some of the other ones may not, or may not occur to the extent that you would think. That's why I always have to tell you when to shift. So I always start with this one because I know this one worked by mistake, because I grabbed the wrong bottle, but they ended up with the same product. And usually the young scholars at OU just kind of go with what you tell them if they're there in class or lab. I know it may be it's different now probably than it was back in those days. But it works. This does happen. Okay. So this is a primary system. You got to shift and you have to shift and lose the halide. Okay. They both have to occur at the same time. I forgot this. Yeah. Otherwise, that's no problem. That reaction's no problem. I forgot the CH2. Okay. So, what other kinds of shifts do we have? Let's say that I had a chloride, this chloride, and I was again reacting it with water. And I said, let's write the major product of this reaction that results from rearrangement. Okay. So I come back and I'm using my same rules that I did before. I look and I see, okay, this is a secondary system. I can go ahead and I can lose my chloride. That's going to give me a secondary carbocation. I now look at hydrogens or methyl groups that could shift. So this is still kind of my alpha carbon. I'm going to look at the beta carbon, see is there a hydrogen or a methyl group that I can shift to make a more stable carbocation. And so I look and I say, well, which hydrogen am I going to lose? The one on the left or the one on the right? And it's going to be the one on the left. I'm going to lose the one on the left because if I lose the one on the right, I make a primary carbocation, which is number 1 forbidden and number 2 not stable, not more stable. Tertiary is more stable. So this hydrogen is then going to shift over. And notice my arrow is not going to the bond. My arrow is going to the carbon because that's where the pair of electrons is going. The hydrogen shifts over, so now I have the plus charge on the tertiary position. The hydrogen is now shifted. And so this is why it's called a carbocation rearrangement, or it's called a hydride shift. And so now I have my carbocation, my water will now come in and add, and after 2 steps again, the addition of the water, the loss of the proton, I'm going to end up with that as my major product, as my major rearranged product. Julia?
How do you know when to shift a methyl versus a hydrogen?
Rule number 1. So rule number 1 dictates what you're going to shift. Okay. So let's look at this problem in that context. But does everybody kind of see what I'm doing here? So if you were questionable, if you wanted to question, well, should I shift the methyl group here or should I shift the hydrogen? It's really a question of rule number 1. So if the hydride shifts, I end up with a tertiary carbocation. Down here, if the methyl group shifted, what would it look like? So if the methyl group shifted, the methyl group would have shifted over and the plus charge would be there. So if I picked up this methyl group and I shifted it over, I would end up with what kind of carbocation? Secondary. Did I obey rule number 1? I went from secondary to secondary. Did the carbocation get any more stable? No. And so you will not end up with a methyl shift here.
Is there ever a case where the methyl shift is better than a hydride shift then?
Well, yes, but not with these systems. Because given the numbers game, if the methyl shifts, you're always not going to end up with if you're going secondary, tertiary, which is all you can do, we can't go primary, tertiary, right? Because there's no primary carbocation. We have to shift and lose at the same time. So if I lose a methyl group, that's automatically going to be a secondary carbocation. Now, Yeah, I don't know. Let me think about if there is one. I should hold on to it for the next exam, but I'll think about whether I can come up with that problem.
Are you just like forced to do it if, like, for example, above that H was a CH3 instead? So in order to go from like a primary.
Well, we can go secondary if you want three methyl groups here.
Yeah.
Yeah, that's typically what happens.
So that's when you use one.
That's when you would be forced to shift a methyl, and that's the next one we're going to do. Okay. But is everybody kind of with me here? If you're not, you got to say something. So you'll get a methyl shift if you do something like this. If I did that exact same problem here, and actually here, we'll extend it, make the problem a little bit more difficult. Again, if I'm reacting this with water so that the water needs to react with the carbocation, I would look at this as a secondary system. Secondary system, whenever you have a secondary or a tertiary system, you need to lose the leaving group first. Okay. Sometimes what people want to do is they want to shift and lose the leaving group at the same time. You only shift and lose the leaving group when it's a primary system. If it's a secondary system, you're going to form the carbocation first. That should probably be rule number 3. The idea that if it's a secondary system to start with, you form the secondary carbocation and then you shift. So in this case, I'm going to lose my chloride and form the carbocation. And so now I have my carbocation. The question is, do I have things to shift? And the answer is yes. I could shift to the left. I could shift a methyl group, which would be perfectly fine. I could shift, if you're looking at the right-hand carbon, you could say, well, I could shift a methyl or I could shift a hydrogen. If I'm looking at shifting, I've got to shift to form the major or the more stable carbocation. So shifting this hydrogen over here would end up with a secondary carbocation. I went from secondary, that's not going to happen. If I shift the methyl group up here over, I'm going to end up with a primary carbocation. Don't even entertain that. That's not happening. But if I take a methyl group here and I shift it over so that the transition state would look like this, so again, I'd have a triangle, a bridge between the methyl group, between the carbon it's leaving and the carbon it's shifting to. So if I'm numbering these, let's call this 1, 2, 3. So this is 1, 2, and 3. So the methyl group is going to shift from the what was a quaternary carbon. It's going to shift over to where the carbocation was. And I'm going to end up with the result of CH3 attached to the C, attached to the CH3. Now the carbocation there, carbon 2 in my numbering scheme now gets the methyl group, and nothing happened to carbon 3. So my methyl group shifted from carbon 1 to carbon 2. And I guess I didn't include the specific numbers for this, but this is sometimes also called a 1,2 methyl shift or a 1,2 hydride shift. The 1 and the 2 are relative numbering schemes, so it moves from carbon 1 to carbon 2. I think they're also called Merwin-Pondor shifts or something like that. I remember that from graduate school. These do have names that they never put in books. So going back and putting in our charges then, the delta plus charge would be here, and the delta plus charge would be there. Because the carbocation is moving its positive charge from carbon 2 to carbon 1. And then again, once I form the carbocation, I do my E1 or I do my SN1 by having the nucleophile add to the carbon or having lose a beta hydrogen. So what I'm focusing on is the shift, is the rearrangement. Does that kind of make sense? So I have to tell you when to shift. So it would be good educational practice for me to say, here is what's going to become, and let's just worry about the SN1 mechanism here. So if I said write the major products of this reaction, what would you do? Okay. What would the rearranged product or products look like? So lose the chloride, rearrange, and then add water to it.
But if it did, that would be great.
What are our rules? And the rules would be about the stimulating carbocation. Does that matter in carbocation?
Yeah, but
And then the same question I would ask. So I'd ask the same question. Which one do you think is going to be major or both of them? Okay, did we get 2 products? Did we get 1 product? Did we get 1 carbocation? Okay, so what are we going to do here? First step is to do what? Go ahead. Break the carbon-chlorine bond and make the secondary carbocation. First step. Now, what can I shift? There's an H there, there's an H there, there's a couple methyl groups over here. Yeah, we're never shifting parts of rings. Although that's not true, but for the moment, we're never shifting parts of rings. So, anybody want to shift a methyl group? If we shift a methyl group, we're just going to end up with a secondary carbocation. So we're not shifting methyl groups. Which hydrogen do you want to shift? Do you want to shift the one on the left or the one on the right? All right, let's do the shifting of the one on the left. So when I shift the one on the left, what am I going to end up doing? I'm going to end up putting that hydrogen there. The plus charge moves here. It's a rearrangement, so the hydrogen moves, the plus charge moves in the other direction. Remember, the plus charge is just the formal charge on that carbon. So if you move the hydrogen and you don't know where the plus charge should be, figure out the formal charges of the carbon. Okay, so there's 1 carbocation. If I shift the carbon on the left, what if I shift the hydrogen? What if I shift the hydrogen on the right? What am I going to end up with? Make sense? Everybody see that? See those? So are these both legitimate shifts? According to rule number 1, are these legitimate shifts? Yes or no? Yes? Why? Why are they both legitimate? Ty? And in making the tertiary carbocation, I made a more stable carbocation. So in both of these cases, I've gone from secondary to tertiary. So these are both legitimate shifts. Agreed? So let me ask a question. Which one's more stable? A or B? And I will give you the option of C, that they are both equally stable. Or D, I don't know. I mean, D as an I don't know answer is usually always available. The reason I ask the D I don't know is because if my phone shows nothing but D's, then it's like, all right, then we just need to figure that out. Okay, so what do we have? A, B, C, or D? Okay, we got 11 A's. We've got 2 B's. We've got 4 C's and 5 I don't knows. Okay. So I asked this question simply to take us back to our rules about how do we judge whether a carbocation is more or less stable. How do we judge the double bonds are more or less stable? What is our rule? Tertiary is more stable. The more substituted the double bond, the more stable it is. The key part here is, does it matter what groups are attached to the double bond? Does it matter what groups are attached to the carbocation? So in other words, if it's tertiary, does it matter what the groups are to make it tertiary? Do some groups make it more stable tertiary than other groups? And our rule was that the alkyl group doesn't matter. Okay. But when I asked that question, I knew that we needed to go back over this rule. So it doesn't matter what the alkyl groups are. And maybe when I'm grading stuff tonight, or I'll throw these 2 carbocations up on the computer and see what their energies are, but I'll guarantee their energies are probably going to be pretty close to getting to each other. Because it doesn't matter if it's a methyl, ethyl, what is my phrase? It doesn't matter if it's methyl, ethyl, or 100 carbon chain. They're all the same. So in this case, I'm going to get both A and B equally. And so if I get both A and B equally, I'm going to go ahead and add water to that carbocation to give me that final product. And I'm going to add water to this carbocation to give me that final product. So I'm going to get those equally. I'm going to get this product and this product equally. What? What don't we like? What happened to the methyl group? Typo. That happens a lot. We have a lot of typos. Okay. So just to kind of refresh, if your rule number 1 says shift methyl or hydrogen, well, let me just summarize all the rules here. Okay. Number 1, I got to tell you when to rearrange. Okay. So you're only going to rearrange when you're told, unless you want to be creative. And if you're going to be creative, then you need to tell me you rearranged, and I might give consideration to the fact that you're making up your own problem. If you just say, I want to rearrange this, okay. If I'm in a good mood, I'll go, oh, okay. They're being creative, I'll give them points. And if not, then, there'll be some deduction. But for the most part, I'll tell you when to rearrange, because it's not something that just happens all the time. It's really difficult to find out when this does or doesn't occur. And I think I bought molecules to try and actually see if this when this happens and when it doesn't happen. Or I will give you a mechanism problem and I'll say, here's the reactant, here's the product. And in writing the mechanism, it's clear you have to rearrange something to get to that product. Okay? So that's the first rule. The second rule is that we always rearrange to form a more stable carbocation. So if we're rearranging and we're not ending up with a more stable carbocation, that rearrangement is unlikely to happen. Okay? You only get one rearrangement per mechanism, that's it. It has to abide by rule number 1 and rule number 2. Should probably write these down. Rule number 1, I tell you when to rearrange. Rule number 2, rearrange to form the more stable carbocation. Rule number 3, only one rearrangement per reaction or mechanism. Let's add a rule number 4. Primary systems, you shift and lose leaving group at same time. No primary carbocations. Rule number 5 for secondary or the occasional tertiary system, you're going to lose leaving group to form carbocation, then shift. And people will sometimes still shift and lose in a secondary system. It just depends on the mood I'm in. It's partially correct, but you may not get full credit. So, not now that I've written it down. So, with a secondary tertiary system, you're going to lose form the carbocation and then shift. Primaries, we can't do that. We have no choice. We got to shift and lose. So these are kind of my rules that govern carbocation rearrangements. And in any of these cases, they always produce a one mechanism. And what does that mean? A one mechanism is a mechanism that involves a as opposed to a two mechanism. A one mechanism always involves a one mechanism. Anything we classify as a one mechanism, SN1, E1, they always involve a carbocation intermediate. So they always produce one mechanism, which means that we have a carbocation intermediate. As opposed to a two mechanism doesn't. Right? So what I'm doing is this. I'm broadening out the definition of 1 and 2. Right? In lab this week, we are doing an SN2 mechanism. But how many steps is it? 2. Because I'm taking, and all of this is true for alcohols. I could do this reaction, this exact same shifting and rearranging with an alcohol as well. But I'm broadening my definition out so that a 1 mechanism has a carbocation. Now, if it's SN, how do you know if it's SN1? I did a substitution. How do I know if it's E1? I formed a double bond. But SN1 and E1 always involve a carbocation. SN2 and E2 that we'll get to on Friday do not.
For an alcohol, can it attain the hydrogen that it needs from a hydride shift instead of water?
No. No. So here is an example of a reaction that we also have done in lab. We took this and we reacted it with our friend H2SO4 and heat. We've done this reaction for a few years, but when I did this reaction with H2SO4 and heat, I got 3 alkene products in my GC. I would always see 3 peaks for my alkene. So, 2 of them, well, these are from rearranged and non-rearranged mechanisms. So in other words, I get those 3 different products if I rearrange or if I don't rearrange, doing this E1 mechanism. That would make a really good graded practice problem. The only question is for Friday or for Monday. Let's make it for Monday. So that way I'll write it up and put it on the web. So what I want you to do for this product is write the 3 products and the mechanisms. Some of the products will come rearranged, some of them will come not rearranged. Okay, and we can talk more about this, but this is an example with the H2SO4 and alcohol. All right, so on Friday, what we will do is we will start and end E2, or we'll go through as much E2. I will fix whatever's wrong with the video so that you can take a look at that, and then I'll answer questions that you have, and we'll do some problems on E2. The next chapter in Top Hat is a combination of E1, E2, and so we'll probably do that next Monday, and then we'll move on to alkene reactions. So I'll update where the reading assignments are today, but for Friday it's going to be chapter 10. Okay? All right, if you have questions, throw them up on Piazza, email me. Otherwise, that's what we'll do on Friday.